This lesson is on solving inequalities. We will solve inequalities, write inequalities, and graph inequalities. Our guiding question: how are solving equations and inequalities the same, and how are they different? At the end of this video, you should be able to answer that question. If we look in this first essential understanding box, it tells us that we can use the properties of equality to solve equations, just like we use those. We can also use the properties of inequality to solve inequalities. The key concept shows us what the inequality looks like as an expression, then what it looks like in words, and then what it looks like graphically. If you're looking at these examples, look to see that if it's just greater or just less than a number, we have open circles. These circles here are open when we draw our graph. If we have greater than or equal to, greater than or equal to, or less than or equal to, we have them filled in, our filled in circles when we have our graph. So just be careful of this. In problem 1 here, writing an inequality from a sentence, it asks us what inequality represents the sentence 5 fewer than a number is at least 12. Just like we did when we wrote algebraic expressions, we want to look for keywords such as at least or greater than. In this case, we have at least 12. So the at least is going to indicate greater than or equal to. So 5 fewer than a number, we get our x minus 5, greater than or equal to 12. So you need to do got it problem 1. The properties for solving inequalities are similar to those for solving equations. The solution of an inequality is what makes the inequality true. And you can check that by substituting the value that you find in to the inequality and see if it's true. Note the following difference. When you multiply or divide by a negative number, you have to switch the direction of the inequality symbol. Very important that you remember that. When you multiply or divide by a negative number, then you have to switch the direction of the inequality symbol. The take note box here lists the properties of inequality, and if you read through those, you'll see that they are indeed similar to the properties of equality. So just read through those and think about those. Now we're going to go ahead and look here at problem 2. Solving and graphing an inequality. So what is the solution of negative 3 times 2x minus 5 plus 1 greater than or equal to 4? So first I need to solve or get rid of my parentheses by using the distributive property. So negative 3 times 2x is negative 6x. Negative 3 times negative 5 is positive 15. Plus 1 is greater than or equal to 4. Then I'm going to combine my like terms. 15 plus 1. So I have negative 6x plus 16 is greater than or equal to 4. Then I'm going to subtract my 16 from both sides. Then I get negative 6x is greater than or equal to negative 12. Now I divide both sides by -6. This is our key difference. Note we're dividing by -6, which means I need to switch the direction of the inequality symbol. So I end up with x is less than or equal to 2. And then if I make my graph, I draw my line, making sure we put arrows on the end, mark my 0, put my target number on the side of 0 it belongs on. In this case, 2 is to the right of 0. My symbol includes the equal sign, so I have a filled in circle above 2. And then x is less than or equal to 2, so my arrow points to the left. If you relate this back to the box above, this is what they were talking about when you divide by a negative number. What's going on right here, where you need to make sure you switch the direction of your inequality symbol. Now we're going to look at a problem where we use an inequality to solve a real-world situational problem. So if we look at this problem, we want to read it first. It may help you to underline the key facts. 36 a month and rent as many movies as desired. Or you can pay $15 a month and $1.50 to rent each movie. Okay, so I'm talking about the two different subscription plans here that a movie rental company offers. So what they want us to find is how many movies must you rent in a month for the first plan to cost less than the second plan. So let's go through our steps here. First, we want to assign a variable. The thing we're looking for here is how many movies, how many movie rentals in 1 month. So let's let that be M. M equals number of movie rentals. Second, we're going to write an expression for the cost of each plan. The first plan, you just pay $36 a month. So just 36. The second plan, you paid $15 a month, plus you paid $1.50 per movie that you rented. We can write $1.50 as just 1.5 M. So that would be the expression for that. Now we're going to take the two and we're going to write it the way they want it to be. The first plan must cost less than the second plan. So if we take the first plan, 36, I want to know when it's going to be less than that second plan, 15 plus 1.5 M. So then I'm going to solve it. So if I solve, I subtract my 15 from both sides. And I get 21 is less than 1.5 M. And then if I divide 1.5, divide both sides by 1.5, 21 divided by 1.5 is 14. So I get 14 is less than M. So let's relate this back to what it's actually saying. Okay, sometimes it's easier to understand if we can write it with the variable on the left. So I'm going to take this, put my variable on the left, my number on the right, and since I changed their places in order for the equation to stay the same, I need to make sure my inequality symbol is still pointing to the same number that it does in my answer, which means it points to the 14, because what it's really saying is m is greater than 14. So my actual answer here is I must rent more than 14 movies. More than 14 movies. For the first plan to cost less. Okay, other than that, if that's not the case, then my first option would be my better option. So whenever we solve one of these, then we need to give the solution in what makes sense. Just like with equations, with inequalities also, there's always three possible things that can happen. Either we get a solution. In equations, we're going to get one solution, which would always be true. Okay? Now in inequalities, if we get a variable less than or greater than to a number, then that means that it's sometimes going to be true. Or our variable disappears in the course of solving our problem, and we end up with the true statement, in which case it will always be true. Doesn't matter what value of the variable there is, it will always be true. Or if our resulting statement is false, then it will end up being never true, which means I have no solution. There is no number that will make it true. And if we look at this problem 4, it shows us those two examples here. If I look at example A, I go through the steps of solving it using the distributive property. And then we see here we have negative 6x on both sides, which if I add 6x then to both sides leaves me with negative 2 is greater than 7. Is negative 2 greater than 7? No, it's not. It is false. So that means that that inequality will always be false, so therefore it has no solution. So it will never be true. Example B, if we do our distributive property and then combine our like terms, we see here that 3x is what I have on both sides, and if I subtract 3x from both sides, I'm left with the statement negative 15 is less than or equal to 8. That inequality is true. So that means this inequality will always be true. So all real numbers would be our solution. I would like for you to try God at problem 4 now. Back in Algebra 1, we solved inequalities, and we also solved compound inequalities, which, if you remember, there are two inequalities that are joined by the word and or by the word or to form the compound inequalities. When solving a compound inequality containing and, you want to find all the values of the variable that are going to make both inequalities true. So that means we have an intersection graphically of our solutions where the two different inequalities overlap so that both of them are true. So if we look at problem 5 here and we solve each one, we end up with x x is greater than 3, which we show graphed right here. and x is less than or equal to 6, which we show graphed right here, where if you look, our intersection point ends up being between these 2 points. Now, we need to be careful here because this inequality symbol should have an open circle around it because our symbol here is less than. And this one should have our closed circle because it includes the equal sign. So our final graphic solution would be this. I would like for you now to try Got It's problem 5A and 5B. We can collapse a compound inequality into a simpler form since the x plus 1 part of this is the same in both. We're able to put the x plus 1 here in the middle, put the smaller value 5 on the left-hand side because smaller values are to the left of the number line, and the larger value 13 on the right since larger values are to the right side of the number line. And we can write that as this, and you would read it as x plus 1 is greater than 5 and less than 13. Some people can look at that and they can see that overlap solution. They can see it more easily when it's written like the collapsed compound inequality. Other people like to solve them separately. So whichever way you prefer is okay. The last thing we're going to look at is solving a compound inequality containing OR. If you think about what the word OR actually means, if I have two different inequalities, it means this could be true or that could be true. So what that ultimately means is you just graph both inequalities and then look at the graph and interpret what it says. So if I look at problem 6 here and I look at the two different inequalities, first I solve the first one and I get k is greater than or equal to -1. Then I solve the second one and I get k is less than or equal to -5. So now if I look at that graphically, I see that k is greater than or equal to 1 looks like this. And I see that k is less than or equal to 5 looks like this. So then on my number line, I just graph them both and I can see that a solution makes either inequality true. As long as a single solution makes one of the two inequalities true, it satisfies my conditions for an OR inequality. So now I would like for you to try the Got It problems 6A and 6B.